Whenever we dream about interstellar travel, there's always this one big problem that pops up, right? As you get closer to the speed of light, your mass supposedly balloons up, making it impossible to go any faster. It's that classic roadblock from Einstein. But is it the real roadblock? In this explainer, we're going to dig into the true energy cost of zipping around the cosmos, and you'll see that the real problem has been hiding in plain sight the entire time. So this whole idea of relativistic mass gain, that you get heavier the faster you go, it's become the popular villain of interstellar travel stories. But is that really what's stopping us? Is that the thing that makes the energy bill for a trip to the next star system just so unbelievably high? Let's find out. Okay, here's how we're going to break this down. First, we'll look at that whole relativistic weight gain idea. Then we'll see what happens in good old Newtonian territory. After that, we'll figure out exactly when Einstein's tax really starts to kick in. We'll even take a look at nature's own speedsters for a reality check, pinpoint the actual barrier for humans, and wrap it all up with the final brutal equation. All right, let's dive right into our first section, the relativistic weight gain. It's time to draw up the itemized bill for our cosmic road trip. Now let's start in what we can call Newtonian territory. Our first stop is going to be 1% of the speed of light. Now that might not sound like much, but it's still about 3,000 kilometers per second. So let's see how much of a penalty relativity slaps on us at that speed. To figure out that penalty, we need this little mathematical tool right here. It's called the Lorentz factor, and it's usually represented by the Greek letter gamma. This thing is really the heart of special relativity. See, when you're just standing still, gamma is exactly 1. But as your velocity, v, gets closer and closer to c, the speed of light, gamma starts to grow, and that's what causes all those wild relativistic effects. So after we run the numbers for 1% of light speed, what's the relativistic surcharge? Well, get this. It's a tiny, almost laughable 0.005%. That's it. At this speed, Einstein's tax is, well, it's basically a rounding error. It's practically nothing. And this chart just says it all, doesn't it? Look at that energy bill. The huge, overwhelming part of the cost, the base price, that just comes from old school Newtonian physics. The basic energy of motion. And that little relativistic surcharge? It's that tiny, tiny sliver at the very end. The real engineering problem isn't relativity, it's that the base price is already massive. Okay, on to section 3. When does Einstein's tax actually kick in? So we saw that 1% of light speed is basically Newtonian territory. Let's really open up the throttle, push it to 10% and then 25% of light speed, and see if the cosmic tax man finally shows up with a big bill. What's so wild here is just how slowly that tax grows. I mean, at 10% of light speed, relativity adds less than a single percent to the total bill. And even when you're going at a quarter of the speed of light, which is just insanely fast, it's still only a 5% surcharge. Newton's physics still gets you 95% of the way to the right answer. So this gives us a really useful rule of thumb. Basically, for any speed below about 30% of the speed of light, relativity is more like a small correction, not some huge dominant force. The idea that Einstein just slams on the brakes as soon as you start going fast, it's really a bit of a pop science exaggeration. The real villain of our story is hiding somewhere else entirely. And here it is. Here is that villain. Let's just forget about relativity for 1 second. The classical energy, just good old 1/2 mv squared, the energy you need to get a 1,000-ton ship to 25% of light speed, is 7 times 10 to the 20th joules. That is roughly the entire annual energy consumption of a country like Spain or Australia. The base price is already completely absurd, and that's before Einstein even adds his little 5% tip. Okay, these speeds can sound a little abstract, so let's get a reality check. Let's look at nature's own cosmic speedsters. I mean, does anything in the universe actually move this fast? Seriously, think about it for a second. We're talking about mind-bending velocities. Where would you even find them? Well, the answer, maybe not so surprisingly, involves the most violent, energetic events the universe has to offer. So, when a massive star dies, the matter falling into its core can hit about 25% of light speed. When 2 neutron stars smash into each other, they blast out debris at 20 to 30% of light speed. These are some of the biggest explosions we know of, and they all operate right in this exact speed range we've been talking about. And this gives us a pretty fascinating insight, doesn't it? It's like nature itself has this sort of practical speed limit of around 30% light speed for throwing big chunks of matter around. And isn't it interesting that this is right around the point where our rule of thumb says relativity goes from being a minor footnote to being the main story? So if the physics of getting heavier isn't the real showstopper, then what is? Well, when we start talking about sending people to the stars, the problem kind of shifts from pure physics to biology and engineering. It turns out it's not about how heavy we are, it's about how fragile we are. And this right here, this is the core misunderstanding. We tend to think the problem is the mass of the astronauts themselves, but it's not. The real problem is the absolutely mind-boggling mass of the shielding you have to wrap around those astronauts just to keep them alive. I mean, just think about the real challenges. Accelerating at a nice, comfortable 1G still takes you about 70 days just to reach 20% of light speed. Oh, and you have to slow down at the other end, right? That instantly doubles your energy budget. But here's the real killer. At those speeds, a single grain of interstellar dust hits with the force of a weapon. Protecting your crew from that requires tons and tons of shielding, and that extra mass is what makes the energy numbers truly impossible. The problem isn't the crew, it's all the stuff they need to not die. And so we arrive at our conclusion. We went into this looking for a complex, exotic villain hidden away in Einstein's equations. But the real monster, the thing that makes interstellar travel so incredibly hard, was hiding in plain sight the whole time, in a formula you probably learned in high school. And this is the ultimate takeaway. The energy problem isn't some tricky relativistic tax that suddenly crushes you at high speed. It's the fact that the base price, the classical kinetic energy, is already so absurdly astronomically large that it makes almost every other problem look small. Before we can even begin to worry about Einstein's speeding ticket, we have to figure out how to pay the gargantuan toll just to get on the cosmic highway in the first place.